Hello, in this video we're going to be talking about Math 3 Unit 6, Objective 6, proving the Pythagorean Theorem algebraically. In middle school, your students had lots of experiences with the Pythagorean Theorem, hopefully including proving the Pythagorean Theorem in several different intuitive, informal, mostly geometric ways. But now they have the algebra skills to see some beautiful algebraic proofs of the Pythagorean Theorem, and in this unit is a perfect time to come back to that. And so if you have time this year, this would be a fun activity to do. Schools are choosing which parts of Unit 6 to cover. This may or may not be one your school chooses to look at this year, but I'm just going to look with you at this assignment. Let's see if I can make it a little bigger so you can see better what's going on. Okay. So this together is notes. When you print the work, it will start with notes and notes. And having talked through that geometry with them, this is homework that the first page based directly on what you just did in notes, and it's one algebraic proof. And then there is an answer page for you that you can print. It's a separate document. For that key, it's a key to page 1 of the homework. And then there is one other proof for them to do for homework. And so we're going to look at those together and see what we have, just so you get the idea. So the first page here, let me just do one page at a time so I don't accidentally write through. This first page, we're just going to reactivate the geometry in their brain that they haven't accessed in a while, make sure they get that. So we're going to start. I would have students, I would maybe read or have somebody read this little first paragraph talking about James. We're going to study James Garfield. He was a president of the United States. This was his own proof of the Pythagorean Theorem. He did this math as a relaxation from the stresses of presidency. He found math relaxing to be able to do. So then I would have maybe a student read each step and have them find what they're talking about. So this first step says we start with the right triangle QRS, where QR equals X, RS equals Y, and SQ equals Z. Label the sides of the triangle with their respective lengths. And thank you, Susie, for reading that for us. And now I'm going to label QR as X, RS is Y, and SQ is Z. Perfect. Okay. Joseph, read this next part. Okay, next we construct QT. So QT is perpendicular to QS, and QT is equal to QS. So they did the construction for us. We're not going to pull out our compass here, but they constructed it to get a perpendicular and equal. So we're going to label QT with the appropriate length. So QT is perpendicular to QS, and they did the perpendicular for us, and it's equal to QS. So QS I see is Z here, so this would also be Z because they're equal. Good. Okay, now Stephen's going to read. So now we extend RQ and construct TW. So TW is perpendicular to RQ, creating TWQ. Mark the right angle formed by the perpendicular lines. So, thank you, Joseph, for reading that. Let's see, so I'm going to translate as teacher. They extended RQ, so they kept it going up, and they constructed TW. So here was T originally, and they're just going to keep this line going up, and then they're going to make TW be perpendicular to RQ. So that would be, this was a right angle. TW is perpendicular to RQ. So there we go. Mark the right angle, so we have that marked. So now we have all of those things done. Back side of the notes handout, or you could just, if you don't make this a handout, you could have them watch, but I think it's kind of nice for them to have it right in front of them. We know that triangle QRS is congruent to triangle TWQ by angle side. Mark equal angles in the picture. Okay, so let's see what equal angles we have. This is QRS is congruent to TWQ by angle side. So let's figure that out. So I see that they both have right angles, so those are equal. And now I need the other equal angles. So these two aren't necessarily equal to each other. but these two together add up to 90. So I'd point out that those two together add up to 90. If you wanted to label them, here, let me just put little marks. If I wanted to label this angle 1 and angle 2, I know that angle 1, if I was writing a proof, plus angle 2 has to equal 90 degrees. I actually also know this angle up here. Let's put some more numbers on these. I know that angle 1 plus angle 3 has to equal 90 because the angles in the triangle have to equal 180. So these two have to be the other 90. And so because of that, I should be able to prove, if I wanted to write a formal proof, that 2 and 3 are equal to each other. The formal proof, for those of you who just would love to do that, would be by substitution. I could have 1 plus 2 equals 1 plus 3. And then by angle addition or angle subtraction, I can subtract off angle 1s, and I would eventually get that angle 2 is equal to angle 3. So it turns out that there's one pair of equal angles. And then by a similar argument, I could get this being a second pair of equal angles. They fortunately did not ask us to write a proof. We just need to kind of convince ourselves which ones were equal to what. So now we know. And so now use corresponding parts of congruent triangles to discover and label the lengths of side QW and TW. So QW is between the right angle and the one I have marked twice. So that would be this side. So this would be a Y. And TW is between the right angle and the one I have marked once. So that would be this side. So this would be an X. So all of that to get the X and the Y. And the last thing we're going to do is construct TS to connect points T and S. So they just drew that line in. What can you conclude about this quadrilateral? So this would be an interesting thing. The quadrilateral is RSTW, this great big quadrilateral. What do we know about that? Well, it doesn't look like a rectangle. It doesn't look like a square. As a matter of fact, I can see the sides are not equal in length. Doesn't look like a parallelogram because I don't have two pairs of opposite sides that are parallel, but it does look like it has one pair of opposite sides are parallel. How could we know that? Well, we could know that because they are both perpendicular to the same line. Or if we wanted to take it this way, we could say same side interior angles were supplementary. But since they're both perpendicular to this line, RW, they must be parallel to each other because they're all in the same plane. And so I could conclude that it's a trapezoid. That's what I could conclude. Again, fortunately for us, they're not asking us to write any proofs, but we are kind of thinking some geometric thoughts that are far away from when your students did them last spring in Math 2. No, last fall in Math 2, a year ago. And so it's good to kind of think through these things with them together. Okay, now that we know that's a trapezoid, now we're ready to do the proof. And so I'm gonna just move this over with the completed info. No, yeah. So here's the diagram and here's the info. What's the area of QRS? So QRS, 1/2 base times height would be 1/2 y times x, and so that would be the area of that. What's the area of TQS? Well, TQS is this guy, and so that would be 1/2 base times height, so it would be 1/2 z times z. There we go. What's the area of TWQ? That one should be the same as our original because they're congruent, but I could do 1/2 base times height. If I would turn the paper a little bit for them, they could see that better, and that'd be 1/2 xy. So the total area would be these three things added up. 1/2 xy plus 1/2 z squared plus 1/2 xy. These two like terms add up to xy, or 1xy plus 1/2 z squared. Now remember that we said it was a trapezoid, so what's the formula for the area of a trapezoid? You might need to remind them. It's 1/2 the height times the sum of the bases. 1/2 base 1 plus base 2 times the height is how I remember it. And so the height here would be x plus y. That's the height. It's perpendicular between the bases. That's the height. Base 1 is y. Base 2 is x. So when we put those in here, 1/2, the height, this is my height. This is base 1 plus base 2 And when we multiply that, or put that all together, we get 1/2 x plus y quantity squared. So these are two different ways to find the area of the exact same shape, by adding up the three separate triangles or by looking at it as a whole. So when we added up the three separate triangles, we got this piece. When we look at it as a whole, we got this piece. And now the proof will come in setting those two things equal to each other. So here they have the sum of the triangles and the area of the trapezoid, and students should now be able to continue working through. It is a little annoying how you continue to have that half going through, but when you work that out and multiply through by 2, you get exactly the Pythagorean theorem. By the way, I can subtract this from both sides. I definitely can, because I know for a fact that these are equal. I'm not proving that they're equal. I know they're equal, so I can use adding and subtracting things, addition property of equality. I can add or subtract things for both sides. So when they're proving something, I don't like them to move from one side to another, but this one is done. Okay, so that is that first proof. And the second proof that they have, there's many different proofs. The following diagrams develop a proof. I would have them add C on here. I believe C was on there originally, and somehow my graphic is not so great. So it says arrange those 4 triangles as shown. So if we had those cut out, we would move them just like this, and these guys would all be C. Explain why A, B, C, D, the big one, is a square. And I would write down in words that it has 4 right angles and 4 equal sides. Each side is A plus B long. Okay. What can we say about EH, or why can we say that EH is equal to EF is equal to FG is equal to GH, and that's all C? Because those are all the hypotenuses of congruent triangles. Those should all be the same. And so we know that all of those sides are equal. Does that mean for sure that this is a square? Well, not really. We need to know that the angles are equal also. We need to know that those are right angles, or that the angles are all equal as well. And so let's check that out. I think we might still want to be able to see that diagram. Using the angles of the right angled triangles, explain why the 4 angles, these 4 angles right here, are right angles. Explain why these are right angles. And my argument would basically be that if I call these 3 angles, and if I call that on every single one of them, that the small one is 1 and the larger one is 2, so I put 1 and 2, 1 and 2, 1 is small, 2 is large, because they're all congruent. I know 1 plus 2 plus 90 equals 180. And so here I have 1 plus 2 plus something, definitely equaling 180 because it's a straight line. So this would have to be 90. So since 1 and 2 and 90 add up to 180, and here I have 1 plus 2 plus something adding up to 180, that would have to be 90. They need to explain that in words somehow. I would maybe help them by numbering angles so that it makes it easier for them to explain. What can we now say about this interior quadrilateral? It's a square because it has equal angles and equal sides. What's the length of each side of square ABCD? ABCD is this big one, and that square is A plus B. So all of that was just to show this was a square. And now what's the area of ABCD in terms of A and B? So the big square would have an area of A plus B squared, and then this is in factored form, factorized because it's an Australian worksheet that I stole, and so that's how they say in Australia. And then in expanded form, expanded is A squared plus 2AB plus B squared. You can help your students with that math. What's the area of each of the triangles? It's 1/2 base times height, so that's 1/2 base times height, or 1/2 AB. And the area of that big giant square can also be found from 4 triangles and a square, right? 4 right triangles plus 1 littler square. That would work. And so we're going to use that to write another expression. And so I would say 4 of these right triangles plus the square, which was c squared, would also work. And simplify as much as possible. So if I go 4 times a half, I'm going to get 2ab plus c squared. So the expressions we obtained in 6 and 8 are the same area, so they are equal because it's the same square. So it says, with this, you should notice there's a term on each side which is the same. We can put them equal to each other, so I'm going to put them equal. A squared plus 2ab plus b squared equals 2ab plus c squared. We know they're equal because it's the same shape. We can subtract that term from both sides, so if we subtract the 2ab from both sides, lo and behold, we get a squared plus b squared equals c squared. Explain in your own words what you've now proved. So lots of kids might write, I'm sorry, I was off the screen. I apologize deeply for that. So here's where I did 4 times the triangle area plus this square's area, and I got this. And here's where I put 6 and 8 equal to each other, and I subtracted 2ab from both sides. And now some kids might say they got the Pythagorean theorem, or some kids might say the Pythagorean theorem's in word. The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And I probably would be okay either way. So anyway, that's that last assignment. And so I give you lots of opportunities to decide which parts of Unit 6 you're going to do. I would advise overall that either you're going to do 6-1, 6-2, 6-3, and 6-5, not including number 2. Or you're going to do 6-1, 6-2, 6-3, and 6-6. Notice both times is not 6-4. Or if you need something shorter than that, you could skip 6-2. Or if you need something really, really short, you could do just 6-1 and 6-6. Although, wait, I was trying to, apologies there. 6-2. Am I kidding? This one, or you could do 6-1, 6-2, 6-5, and 6-6. This one you'd skip number 2 again. If you were trying to shorten that more, you might skip 6.2. If you're trying to shorten that even more, you might skip 6.6 and just have these 2 as for a very, very short thing. I feel like if you just jump to 6-5, that's going to be a big jump, and so 6-1's kind of at least a nice lead-in for that. So anyway, I wish you the best of luck as you're deciding what to cover out of this unit. Again, the main purposes of this unit were to increase algebraic fluency and to understand the purpose of algebraic proof, and to be able to use the skills we learned in especially units 4 and 5, or 3, 4, and 5, to be able to prove things are true. So I wish you the best of luck. Have fun.